Hi, hello and welcome for today's video. And today we are going to be talking about cracking of wrong chain hydrocarbons. By the end of this lesson or this video, you're supposed to understand what is cracking, why we perform cracking, and what are the conditions that are necessary for cracking. Now, to help us do that, I have this molecule here. It's an organic molecule. As you can see, it has got 1, 2, 3, 4, 5, 6, 7 hydrocarbons, 7 carbon atoms, and these carbon atoms are all joined together by a single covalent bond. So this one is a heptane. Hep means 7 and N because it is an alkane, whereby all the carbon atoms are joined together by a single covalent bond. Now, this molecule is a wrong chain hydrocarbon. These molecules, which are very wrong, they have a very low flammability. So they are very useless as far as fuels are concerned. They don't burn that easily. So the molecules that burn quite easily are the molecules that are shorter, hydrocarbons that are shorter, 3 carbons chain, 2 carbon chain, 1 carbon chain, and so on and so forth. So for us to be able to make these shorter hydrocarbons from wrong chain hydrocarbons, we do what we call cracking. And this cracking, there are some conditions that are necessary for us to be able to actually stopping this molecule. And these conditions are very high temperatures. For example, when you're using temperature only, you go to up to 700 degrees Celsius. Or you can use a catalyst and lower temperatures. When you use a catalyst, that is a mixture of silicon 4 oxide and aluminum 3 oxide plus 450 degrees. The catalyst will increase the rate of reaction. It will move very fast. And hence we reduce the amount of heat that is used. So in our case here, we are going to use a catalyst for us to be able to chop this molecule into a shorter hydrocarbon, into a shorter alkane, and also we form some alkene alongside the shorter alkane. Now, what happens here is that once this reaction starts, this is going to be chopped like that. It's just actually chopping from this end here. Now we have a hydrocarbon that is having three carbons here, and because carbon has to have 4 bonds, we're going to remove 1 hydrogen there. Now we are reorganizing our atoms here in these molecules. Now for this molecule here, now it's going to be reorganized like this. Now, as you can see that molecule, we have here we don't have a hydrogen, here we don't have a hydrogen. So these are potential areas where we can have both. These are a free electron, and this one represents a free electron where we can form a bond. Now, because we don't have any hydrogen atoms anywhere, what is going to happen is that this carbon atom having an extra electron here, which is free, and this one, they are going to form a double bond here. So what happens is, we are going to replace this one now with a double bond, like this. Such that now, we have a molecule now having a double bond here, and this molecule now qualifies to be an alkene. Remember, alkenes always have a double bond. Now, this one, because it has 1, 2, 3, 4, it has 4 carbon atoms, it becomes a but. And because it is an alkene, so we form an alkene there. This one now has all the atoms joined together, carbon atoms joined together by a single covalent bond. So this one is an alkane. And because the carbon atoms are 3, it is an propane. Now, you can see now, from our original heptane molecule or a wrong chain heptane molecule, we have been able to form this molecule here of an alkane, which is having having very few number of carbon atoms, which are 3, and an alkene here. So this molecule here is more beneficial. It can be used in petrol, kerosene, jet fuel, and so on and so forth. Thank you very much for watching this video. We are going to perform more of this for other longer chain hydrocarbons or alkanes, and see how you produce more shorter hydrocarbons which can be used in fuels and so on and so forth. Thank you for watching this video. I hope you have benefited. Remember to comment and subscribe, and we meet in the next video.